Welcome to this video on center of mass, center of gravity, and torque. This is a very interesting topic, and a lot of people will say that center of mass and center of gravity are the same thing, or will ask, are they the same thing? And they're not the same thing. I think the main reason that they get interchanged so often is that they're at the same location in a lot of the problems that you do in early physics situations. So I'll say that again. Center of mass and center of gravity are not the same thing, but they oftentimes end up being at the same location in an object when you do some sort of intro physics or early physics topics. But let's take a look a little bit at how they differ, because it's actually really cool and very interesting, and it'll make a lot more sense, I think. So here I have a rectangle, and some of the assumptions I'm making in this video are that all the shapes I'm talking about have what we will call a uniform density. Okay, that means that at all points the density of the object is the same. Now in the next few videos I will take a look at non-uniform dense shapes, and we'll look at how to deal with those situations using calculus. So uniform density, and we're going to say that they are what, for lack of a better term, are called regular geometric shapes. So regular geometric shapes are shapes that are either symmetrical, where we can have a centroid easily drawn where the center of mass would be located. So they would be at the same place. So the center of mass is going to define a mean position or an average position. So the mean position of the mass of the object, or the matter in this object. Now it can be beyond just being an object, it could be for a whole system, and we'll look at that in subsequent videos. So this is the mean position of the matter of the object. And that's how we're going to define it right now. Now, if you have a uniform density and you have a regular geometric shape, the mean position of the matter and the centroid happen to be the same thing. So I could draw a diagonal here and another intersecting diagonal here approximately, and that's my center of mass and my geometric center. Now, is it also my center of gravity? If this box is uniformly dense, it's regular, and it's on Earth at the position we are right now, yes, they'd be the same place. They're not the same thing, but they would be at the same location, and I could essentially treat them as the same thing, but they're not, okay, and we're going to see why. Next, let's look at this. This is just an interesting topic about how this thing would turn. So we're already seeing here there's a pivot has been established on this corner, okay, in these subsequent pictures. So I'm going to keep the center of mass here is staying the same, okay, in the same approximate point, all right, and the center of gravity is the same thing, okay. So essentially what we're saying is, because this object is uniform, and it's at a position where at every corner of the object, for lack of a better descriptor, or every position in the object, the force of gravity on all of those positions is exactly the same value. And so essentially what it's saying is that the force of gravity is really only just acting over here at the center of mass. So the object will act, okay, the object will act as though the force is only acting at the center and not at the four corners, okay. So that's essentially what it's saying, is that the force, the center of gravity, is defined as the mean position of the force of gravity acting on the object. So if it's the same at all points, then it's going to overlap with the center of mass. Okay, the base of the object over here, okay, we can think of the shadow that it would cast onto the ground. So in this case over here, it's going to cast a shadow onto the ground. I'm going to call this the base, and we're going to see if we look at the center of gravity of the object now, not just the center of mass, we'd see that the object's going to get pulled straight down, as if it were only all the mass were located at that point, because it's evenly acting at all the corners. Just a little sort of side note, this is called unstable equilibrium. Okay, and the reason for that is that it's not entirely stable like this one is, but it's going to go back to being stable because the force is going to pull where it's over the base or the shadow of the base, okay, relative to this pivot point, and it will wobble a little bit, but it will rectify itself in this regard. Now, if I look at this picture, again, the center of gravity, that's, remember, that the mean position of where the gravitational force is pulling or acting, is still in the same place, and it's still the same value, and it's still pulling straight down in all of these examples. There's no change to that, okay? And now we see that this base over here, this shadow of the base, right, the gravitational force is no longer above that, and so the object is going to experience a torque because now there is a R value between the pivot point and where the force is acting, and this thing will fall and it will become back to its original position. So this is going to just be called unstable. This is no longer at equilibrium at all. It can't rectify back to its original shape. So the cool thing about center of gravity opposed to center of mass is that the center of mass is the same here in all positions, because remember, the mass isn't repositioning itself. It's not redistributing throughout the object. Additionally, because the gravitational force is the same at all points on the object, it's not changing either, and that's how the object will rectify itself. But what if you had a situation where the center of gravity was not at the same position as the center of mass, and what would that kind of look like? So I'm going to go to a really extreme example first, but there's a lot of non-extreme examples that you might encounter. So what I'm going to do here is I am going to take us out to space, and we're going to see maybe just the edge of the Earth here on the horizon. So we're kind of far out. And I'm going to take this long beam, let's make it a different color, this long metal beam, and it's going to be out here in space. And I'm going to say that this is uniformly dense again, so its center of mass is going to be right here at its geometric center. So this I'm going to call M for the center of mass. And what I'm going to do now is I'm going to go ahead and copy this object and paste it, and then I'm going to rotate it a little bit. So I'm going to rotate it about 45 degrees one direction. Okay, now I'm going to have to scoot it up a little bit so it's not hitting Earth. But it's exactly what I want, because what I can see now is that the gravitational field at all points on this object right now, so here's the center of mass because I shifted it, is different. Here it's super close to the Earth, so it's going to have the gravitational force over here because of the gravitational field, right? So let's say the field right here is at 8 newtons per kilogram instead of 9.8 because we're some height off the Earth. But way out here, let me pick this point over here, the force of gravity is a lot smaller, and this gravitational force at this point, I'm going to say, is just 5 newtons per kilogram. Okay, obviously these numbers are not necessarily proportional, but we'll keep it this way to make our point. And you can see here now that this end of the object is experiencing a much stronger gravitational force than this end of the object is, and I am going to experience then a center of gravity that's pulled on this object closer towards, so I'm going to label this one big G, center of gravity, closer to the end that is experiencing the stronger gravity, right? And you can think of how this is going to pull this object, right? How that object is going to experience the gravitational pull, and that might create some sort of a torque in the air as it moves. Now, let's think of an example where it would be extreme, even more extreme than this. Let's say that this is the edge of a black hole, okay, or the event horizon, and you have a person here, which this person's really large, proportionately in the picture. And I'm going to say that because the density of this black hole varies so much from the middle of it to the edge of it, that the gravitational field you experience at your head is going to be so much less than the gravitational field that you experience at your feet. So we're going to say that G sub F is really huge compared to G sub H. And what that's going to do is it's going to shift the center of gravity on you closer to your feet. And because you're not staying the same the whole time that this happens, is it's just going to get stronger and stronger at your feet. And the idea is that you would stretch out as you get pulled feet first into the black hole, because the feet are being pulled harder than the head. And this is very scientifically referred to as spaghettifying or spaghettification. But most likely, you wouldn't just stretch because you're not very elastic. You'd probably just break up into lots of pieces. But the main idea is to remember that if all parts of the object experience the same gravitational force, then the center of gravity is at the same position as the center of mass. But if not all points on the object experience the same gravitational force, then the center of gravity will be at a different point to the center of mass, and the object will therefore be rotated because it will be experiencing a force that's greater on one side than the other. And that is the story of how center of mass and center of gravity are different from one another, but oftentimes in our problems at the same position. In subsequent videos, we'll take a look at how to find the center of mass for non-uniform dense objects, and then look at how the moment of inertia, the most elusive term in rotational dynamics, is established.